So, in the galaxy, this is the perfect place to be on the 8th of 8 today. Okay. And a funny thing, I got several messages from, every scientist have some friends that are a bit mystic or so, right? I'm sure you guys have too. And so I got some WhatsApp from some friends that are orthogonal to science that told me today is a very important day. I didn't know, but there is a portal that's opening, an energetic portal that's related to the 8th of 8, whatever. So apparently, it's a good, energetic day to do something good. So today for you, I prepared a trip then to the bulge of our galaxy. So we're going to leave the solar vicinity and we'll go to the inner parts of our galaxy. It looks like it's easy because we are inside the galaxy, but it's not. And so this is lecture 3. And you guys should be very tired, right? Because this is second week already that you are learning so many things. So I hope you can get interest about this lecture because as I put, for every lecture, I have a little title. I put here, new window to the galactic bulge. So if somebody was not here all over around, I don't know anymore. So the lectures, in the first lecture, we discussed the basics tools that we had, then the Gaia, the spectroscopic surveys, the astroseismology. In the second lecture, we saw that there are debris of other things here. We understood a little bit about radio migration. We discussed the gradients, that we can see the abundance gradients and how the stars migrate observationally, right? And then we discussed in the colloquium yesterday, I don't know who was not, it was more about the age of the thick disk and the thin disk, and that also a recent result from my group that we found that the thin disk where the sun is actually much older than what was thought until May. So things are very much on the make in this area. So today is the galactic bulge, and tomorrow is about the super metal-rich stars, so stars that have a metallicity more than the solar metallicity, and therefore they are also clearly not formed here, the migrators also. And the future outlook in the area. What are the new things that we are building to get more data? So let's dive into the bulge. So again, if we look at the Gaia picture, the Gaia image on the sky, maybe we could put the light, a bit off. So when we look to the Gaia on the sky, is projected, just like we look by night, the number of stars per unit of area. And we are now focused on the bulge. And this in latitude and longitude, this will be this square there. Of course, I'm not the one, I need the square on 3D. So I have to dive into the bulge. So, but before I have to let you know one important thing before we go to the bulge. Is that the secular process that we saw in the last lecture, that in the abundance gradients, the stars move around and so on, I said in that lecture, they are linked to what was happening in the bulge and bar. Because the bulge and bar, the bar and the spiral arms of our galaxy create resonances, and due to this resonance, the stars move to another place, right? So this is what we discussed in the last lecture. And we said that the main driver of this radio migration is this bar spiral arms interaction. But another driver is also mergers. In the colloquium, I gave an example of galaxies that are inside our galaxy that we discover, like Gaia Enceladus and Sagittarius. So therefore, we need to understand, that's the point, we need to understand what's going on in the inner part of the galaxy to understand what we are seeing here. Because here we have stars from there that come here. And that's why I say studying the bulge there, in the bulge, and here, by studying the supermetal-rich stars. It's very nice that the stars come here, because when they are here, they are closer, I have more information. When they are there, they are difficult, but I have many, and I have to see if things match, right? So because of that, I have to include this plot here, which is now a chemical evolution model. When you put all the nucleosynthetic families that we discussed in the first lecture, and a star formation history, which is number of stars formed per unit of time along a certain time. You have, we know that for our, this is a simple model, chemical evolution model for a thin disk only. Forget about the high alpha, low alpha, just the thin disk, okay? And we have this, that the star formation history here is given in solar mass per parsecs per gigayear as a function of time. So from the past to today, it's not age, it's time. So we started, and here is at different rings in the galaxy. And this is just to show you that if you are at 0 to 2 kiloparsecs from the galactic center, so bulge, we think we had a very peaked star formation history. You see? A factor of 100 more than here. And then this other star formation, this is logarithmic scale. This other star formation history was every time less peaked and more extended, so more gentle. Yeah. Exactly. So this is not a measurement. This is our prejudice. That's how we think when we say the disk form inside out, the thin disk form inside out. That's what we mean. We mean that the number of stars formed per unit of time in the inner regions is much more fast than here. The consequence of that is that there in the inner part of the galaxy, I can reach a high metallicity quickly. Here, to reach that same metallicity takes longer. This is translated by this. So you see, how you know this? I don't. But when I use a star formation history like this, I can then get abundance gradients in the Milky Way. Remember yesterday, it was yesterday, when I show you the abundance gradients, there was a line, and then there was the point dispersion from this line, which was the chemodynamic. But the line was chemical evolution. That line I obtain because I have this star formation history. Okay? So the constraint I have to this, one of the basic constraints in the Milky Way, is the abundance gradient today. I have to do something with this star formation history so that I get the gradient. Okay? And at 8 kiloparsecs, which is where we are, this curve here, the star formation history here, I have several other constraints for this. I have to match the current gas in the galaxy today at this position. I have to match the fraction of type 2 to type 2a measured. I have to match several things, because in the solar vicinity, I have several things to match. So that curve is the one we trust more, and the rest is an extrapolation of star formation history in order to fit an abundance gradient. But the point you have to get from this, why I'm showing this, is that, and this I'm showing a gradient. That's an effect of this. So this is metallicity radius that you saw before I showed the data. Now I'm showing the curves. And this is at different times. So in this model, this is a simple model only for the thin disk, the old gradient was very steep, and then it flattens to get the value today, okay, which we observe. And this is coming because I have used different star formation history. What is important is that in the inner part, we think we are forming a lot more stars per unit of time very quickly. So you can be an old star with high metallicity. Here, you cannot be, if you're forming with this star formation history, you cannot be old with a high metallicity, okay? Okay. Now, the other theoretical thing I have to show you, remember in these plots of gradients I had the curve of chemical evolution, I had the little points dispersing from the curve. This is where the stars in the chemodynamical model. The chemodynamical is a simulation where we paint the stars with chemistry, with the chemistry of each of these shells, and then we let them disperse, and that we saw in the gradients. So that model, if I look now, let's look here, number of stars, let's look this. If I take the number of stars for that chemodynamical model, here, between 7 and 9 kiloparsecs, so around us, and height from above the midplane, 3 kiloparsec, if I take all those stars, they are like this in the model, okay? And this thing here has to match the observers, the observed metallicity distribution that we have. I will show you in a while. And so this is the distribution we have here in this position. And underneath, in the simulation, I have the burst radius of the particles. In the reality, I don't, but in the simulation, I have. And so if I look to where they were born, if I break this here in the several histograms where the stars were born, so for example, stars born between 3 and 5 kiloparsec from the galactic center. That's their metallicity distribution. Look how metal-rich they get. They are the ones that are making this tail here, more than 3 times the solar metallicity. Oh, let's see the ones that were born here, between 7 and 9 kiloparsec. These are the green stars here. So this is telling me if I didn't have radio migration, and all the stars that I'm seeing here were born here, the metallicity distribution should have stopped here. And we observe, we should, if this whole model makes sense, we should observe metal-rich stars here that are from the inner radius. Okay, now I go here, is still the simulation. Now I plot the number of stars as a function of their burst radius here, okay? And now I plot as a function of age. I have the age in the simulation. What do I see? I see, for example, that the oldest stars in the thin disk here, you see? The red curve, this is the whole thing. Again, this thing. The whole thing here, the oldest stars, most of them came from the inner regions, between 0 and 5 inner regions. The more young ones, they came more from here. You see? They're peaking here, where we are. This is, the green is all the stars around the sun between 7 and 9, again, that I can plot here and in my simulation here. And I'm telling you, the stars that are currently here, they came from all these burst radii. So this is what we call the mix of stars. That's why it matters, because at this position, I have a bunch of stars coming from, especially the old and intermediate ones, coming from the region between 0 and 5 kiloparsec in this simulation, okay? Is this understood? Because this is an important, is the brain of what we are going to talk today, okay? So, what I see here in this volume is a potpourri of what happens in the whole galaxy. This is complicated in our life, but it's nice, because if you have a small telescope, you can observe one of these migrators with high resolution, high signal to noise, and it's nice, because you don't have to go to the bulge. But you have to figure out who is who, right? Okay, so the tip of the iceberg are these, the super metal-rich stars that we're going to discuss in the next lecture more. They are rare, but they exist in this volume. And they are the tip of the iceberg that they came from the bulge. Why? Because there is where I had that star formation history that make old stars metal-rich quickly. You see? That's the idea. Okay, so once I take that plot I just show you, here is number of stars with burst radii. We just saw this now, because I'm looking to the stars that are here. Here is the galactic center. We are sitting here. This is usually the Z, how far we are from the midplane. This is radius, right? So if I do the same thing in the simulation, moving my beam to different places, at each different places, the simulation can tell me what is the mixture, right? And if I had data, I could see if this is true. And that's where we are going to have one day, but we still don't have too many. But right now, we have at least this here. As I showed you before, or in the colloquium, I don't know, these are for the Kepler field, stars for which I have good ages, 25% uncertainty in ages. And for the first time, I can plot the fraction of stars as a function of metallicity, just the same plot I show you, but now data. And I divide in 3 groups of age. And I see that, in fact, the young stars are more peaked with not reaching too much high metallicity stars. And when I get to the most metal-rich stars, they are not the youngest, exactly like the model predicts, right? So this is nice. This is data now, it's not model. So something of the model is working. Where they came from, and that's where we're going to the bulge, because they came from the bulge. Okay, so that's why I like to study the super metal-rich here and there. Here we see them, we need to see if there are. Okay? So today we are there, tomorrow we are here. So let's go there. So here is our map of the Milky Way again. This is the box we are interested today, the inner galaxy, right? You see already that we are going to miss a piece if we use only photometry. However, for these 30 million stars in this box, I have 30,000 for which I have apogee spectra. We discussed this before. So, and I had shown you that when we plot the alpha Verarum versus iron as a function of radius, So from the inner galaxy to the outer galaxy, and from mid-plane up to the mid-plane, we had these distributions. And we are today concentrated here, between 0 and 4 kiloparsecs from the galactic center, and very close to the mid-plane, which is a new place, because before apogee, there was essentially no data there. You see, very little data there. Why there were so little data there? Because of this. This is that box now, okay? I took that box. So now we have circa 30,000, so 26,000 and a half. And this is X and Y, so I'm seeing the galaxy again from above. Focus on the part where the bar is. In the big data set with 30 million, could see the bar very clear. Here I have 30,000. The bar is here, but you need some creativity to see it. But it's there. But we are not going to see the bar like this. We're going to have to compute the dynamics, the orbits of the stars, and the orbits of stars will tell me they are in the bar. But there is some kind of density of stars here. But you see, I'm lacking some, because I'm going with high resolution, so I don't get everywhere. Why don't I get everywhere? So here I'm showing this, the number of stars. But look at this plot here. Galactocentric distance, so the inner 5 kiloparsec, as we said, our box, and up and down from the plane. This is a map of extinction. How much extinction I have in that region. So how much my light is being, cut by this. Extinction in magnitudes. So this is a logarithmic scale. This is a lot, I can tell you, a lot of extinction, even for apogee. Apogee is looking the H-band, so infrared, and so we peer into the dust. But even apogee cannot see here. You see? This is they can see a little bit, but a lot of this part here is going to be missing, because here I have AV very high. Who computed the extinction? Our code, Star Horse, using all the information, as I explained in the first lecture. So here I'm going to still have some extinction. If I was in the optical, I was not even seeing this already. So we are happy, but we need more. But for now, we're going to show what we can do with this. Okay. As I said, in this box, part of what is in the box is, is the blue line here, the box that I'm telling you, the 26,000 stars. This is the distribution in distance, okay? And you see that I want a distance from us now, not the distance from the galaxy center, the distance from us. I want that my sample is in the bulge. So I want the bulge is at 8.2 kiloparsec from here. I want my sample to be picked at 8. However, my box of 20,000 has a lot of stars in front of the bulge at 4. So I'm going from here towards the bulge. I walk, we are at 8. I walk until 4, because I cut, and there I have a lot of stars, because the disk is getting, the distribution is getting more. And by the time, but I wanted to see the ones that are there. I don't want to be spending a lot of, because I want to understand the bulge. I want to be in the bulge. So I need to get rid of them. But I cannot get rid of them easily. I cannot get biased. It's very important that I control the bias of o viés da amostra, the bias of the sums. Therefore, why did we wait for Gaia EDR3 to do that? Because when we came to Gaia EDR3, which is end 2020, the proper motions became good as well. We gain a little bit in parallax, but we gain a lot in proper motion, because there is more time to measure the proper motion of stars. And this is what I'm going to use here. This equation here, I'm using proper motion in 2 directions, and I'm using a magnitude to select stars that are more towards the bulge. This is more technical, doesn't matter, but I just want to tell you, I wait to Gaia EDR3 to have good proper motions to be able to do that, so that I don't have to fully rely on my distance, because the distance could have some systematics, okay? So we are always worried about systematics. We have uncertainties, we control the uncertainties, but maybe there are systematics in whatever sample. This is very important, right? That's why when I talk about age, I talk about age precision, not accuracy. Because accuracy, you said is 10 gigayear, is 10 gigayear. The precision is what you can say, okay, I know it's 10 plus or minus something, but the accuracy is a totally different stuff. And that's why when I have an important result like the one I show in the colloquium, I need to use different samples with different techniques to hold the accuracy. That's why there I use seismology and main sequence turn-off. So same problem here. So there's always this worry in whatever sample you're going to have. So here we are worried about not putting too much VS. So what do? We use this, and we get this distribution here. Now it's good, right? We still are going to have some stars in the disk, but most of our stars are sitting in the bulge, okay? But in astronomy, you always pay a price. And what was we pay a first price. We had 30 million objects in the box. We need the spectra because we need the radial velocity to compute the orbits, and we need the chemistry. So we pay the price to have 30,000 in the box. Now I'm paying another price. I want to be in the center. I have to use proper motion. But Gaia works in the optic. So I pay the price that some of the stars for which I have spectra from apogee, I don't have Gaia proper motions. Which price I'm paying? I'm paying here the price. This is the distribution of our stars in this sample, in the red and in the blue, all stars, and the one that I had Gaia. And what you see here, that at Z-Gal, very close to the mid-plane, I had all stars, but I don't have Gaia. I just show you that close to the mid-plane, we had a AV very high. I don't have proper motion there. Pay the price. So I'm going to pay the price because I want the orbits, okay? So what is the price? Now here I have a box, again, from 0 to 4. By the way, this is historical, this box, because it was in 2020 that disappeared in our paper. So here is 0, so we are on the mid-plane, above the mid-plane, below the mid-plane, but it's still, look, very close to the mid-plane, half a kiloparsec from the mid-plane. And between 0, galactocent distance, and 4. Now I'm from, I'm from the inner parts to here. Look, I have a map of the metallicity in this region. You're seeing a lot of metal-rich stars already pumping up, and some metal-poor stars. Now, the price. Wait, where's the price? What is this? Sorry. The price. You see? I pay the price. No proper motion for those stars. I had this box. I'm going to work now with this box because I need proper motion and there was not. But I want the proper motion for this. So the first part of the paper is for the box. Second part is for the price. But what this will give me is so nice that I will go for it. And in the future, I want more because this is getting very small. You want more. We want Gaia and infrared. Okay? Okay. So, as I said, from Gaia DR2 to Gaia EDR3, I got improvements both in parallax and in proper motion. That's what I need to do the game. And Anna was so lucky that was her PhD exactly happening here. The poor Anna. She did the whole PhD during COVID time, so it was not so easy. Here is, for the two samples we showed, the RPM, we call this the reduced proper motion sample, the one that is really in the bulge, right, where we use proper motion. So if I take this same sample and I look here, the uncertainty in parallax, uncertainty in parallax between Gaia DR2 in red and Gaia EDR3 in this, you see that in parallax, the same sample now has much better uncertainties. You're comparing the distribution of uncertainties from Gaia DR2 with Gaia DR3 for parallax. But look for proper motion, what happened. Huge, okay? So when you work with data, this is the first plot you are going to do to see what is the uncertainties for the sample. And then when you know the data, you say, now is the time for go to the bulge. Now is the time for that. Now is the time to look for the age of the thin disk. And that's the way you publish first. But you need to learn the data, okay?
So some guys here use this Gaia data for DR2 DR3. Could you comment the difference between the two?
Yeah, so the proper motion, you need more time, right? So the more time you have, the better the proper motion is. That's why Gaia and infrared, we want it not to be launched before 2040 or 45. Because you want a second Gaia with a lot of baseline, which because when you compare the both, you will have a gain proper motion enormous, right? So that's what's happening here. And the parallax is not going to change much. It's going to change. Gaia DR4 is coming. Imagine what's going to happen. But this was so nice because it was at the same time that the Gaia release came out, but the Apogee survey was on the moment to also liberate the data of the bulge. Because Apogee started, is this high-resolution spectroscopic data set, started in the north. But to do the bulge, you see better from the south. So we had to wait for Apogee South for having enough stars in the bulge. And both things happened at the same time. You see? That's when you say, okay, I am extra busy, I have to do 100 things, but come on, I have to do Apogee Gaia DR3 now, you know? Is the PhD of Anna now, not later, now. And then we are in desperation, COVID, but we have to find the time. That's why sometimes we are stressed out. But it pays off. Okay, so first thing that paid off. For the box now, I don't need the proper motion here. I have epsilon, so I'm seeing from above where the bar is, right? And I was telling you I couldn't see from the density because now I have less density. But I have the velocity, radial velocities I have because I have the spectra. And when we plot the radial velocity distribution, we see this pattern. This is telling me my distances are great, okay? Because we didn't mess it up. Actually, this was very important to convince the referee of our distance. And we see this quadrupole, which is a feature characterizing the mean streaming motion of the bar, induced by the bar. So this is like a signature that there is a bar in the center of the galaxy. And people had seen a piece here, we saw it all beautifully, okay? And so this, there had been earlier results, but they did not reach the other side of the bar. We reached this, and recently another group using a different data set has also got this. And in the simulations with bar, you also see this. It's beautiful, you see? Okay, but I'm not interested in this today. I'm interested in understanding this. So when we go to that box, and we pass from 26,000 to 3,000, so these are the stars that are very close to the midplane and that have survived my price. I had this dichotomy in the bulge, in alpha Ver versus iron. And this was new, you see? It was very clear, and it's difficult. So we were afraid, maybe it's the disk that's in the front, and that part is disk. You see, that the low alpha is disk. But so when we look in the proper motion, we get less afraid, because the systematic should be better control, and it's still there, okay? The first result, very nice. Now, it comes the complication. And bear with me, because now it's going to be a bit more complicated, but it will be so beautiful that you have to pay attention, even though you are in the second week of these lectures. Now I went from 30 million to 30,000, and I got thousands now only. Now, people say, oh, why do you need more spectra? You have so many. Well, depends what you're doing with them. I don't have many. I am left here with 8,000 stars. This is like, no, not enough. And I'm going to show you why. We take, for these stars here, we can compute orbits. We have the radial velocity. We're going to have to use a potential. That's a complication again, because the potential to integrate the orbits is complicated, because you need to know the galaxy has a bar, there's potential with bar, without bar, the bar like this, the bar like that. So it's complicated, but we go for it, okay? We're going to compute with two different potentials, the orbits or whatever. We're going to try to gauge the uncertainties. But what is important is that we have then computed the orbits for these stars. And then we are in the bulge. I cannot a priori tell you, oh, this is the piece of the thick disk there. This is the piece of the thin disk there. Oh, I'm seeing the spheroidal bulge. No, there is no spheroidal bulge. This is the discussion in the field. There is no spheroidal bulge. Everything is a bar. There is no bulge. There's a bar, whatever. I cannot a priori say who is who. I have to let the data tell me. And how do I tell if somebody is disk or spheroid? The spheroid have high velocity dispersion. I have things that are not with rotation. So these stars are not going to rotate, right? I have, if some star is passing, the Zmax in the orbit could be very high, or could be very, because what I'm showing you, when you look in Z, you're seeing where the star is today, but the star is in an orbit. And the orbit can be the star is maybe here coming like this, or is passing. So I need more. And that's what I'm doing this. So I'm going to take the 8,000 stars and I will throw in this diagram. What is this diagram? The eccentricity in the orbit of each of these stars and the Zmax in the orbit. So a star is in our orbit around the center of the galaxy, and I have orbits that are circular there inside, and I have orbits that are eccentric, but I have orbits that are eccentric or like this at low Zmax, so they are low, and I have stuff that are doing like this, you know, they are high Zmax. How high from the mid-plane? When I say high, is in absolute value, up or below, right? So how far from the mid-plane the orbit takes this star, and what's the eccentricity of these orbits? And yeah? It's defined, okay? I can show you in the paper, yeah. That's the difficulties, that becomes this problem, because you also need the potential to compute this, right? So, and is not anymore an axisymmetric potential, you have a bar, and so you have all these complications. So there are potentials you can use and compute this. So this is the dangers. And actually, when you change the potential that is computed, assuming a bar on another bar, you see that some stars that are here go here. But that's what happens, not that you change a star here to there, you know? So inside the uncertainties, we have to see what can we learn from that. And we did this calculation several times. But here what's important is that these stars are occupying here. This is the number of stars in the sample I have. And I am having a lot of stars at high eccentricity. And, but I have some stars, look here, at low eccentricity. They are like in disk orbits, they're inside, okay? Now I have to see their guiding radius. It's not enough to see the orbit. I have to compute the guiding radius of star. Maybe the orbit is such that the guiding radius is 4 kiloparsec, is 5 kiloparsec. So it's not in the bulge, essentially, okay? So all this I'm gonna tell now. But before we go there, I now plot the metallicity here. I see immediately that stars that are very close to the midplane are very metal-rich. And the metallicity is dropping when I go up. But I have metal-poor stars here too. They are behind. And we're going to see this in a while. But we are seeing that the most metal-rich stars, which are the ones I'm interested to see if they exist somewhere, they are already showing up here. Look the metallicity scale. Solar, 0.2. The stars we were discussing before, right? That here, the solar vicinity, we see stars that are 0.2, where they came from. 0.3, where they came from. And it seems that there are a lot of them there. We are going to find them. Okay, so it turns out that by studying the orbits, we found that in this box we have an inner thick disk, old, like the one we have at the solar vicinity. We have an inner thin disk, which does not reach very the center, just like in that picture I showed you in the first lecture from the JWST. Beautiful. And we have the old spheroid bulge too. We do have. Small, but we have. Now I'm going to prove this that I said. This is the result, okay? So now is the complication. This is always that same diagram. I put it here for you to remember. We are looking the stars in a Zmax eccentricity family orbits. These are the families. A, B, C, D, E, F. I cut this diagram in family orbits. And now I have high-resolution spectra. So now I'm going to look for each box, which is the alpha over iron versus iron distribution of the stars. Now, you see that I have the discontinuity thing here, something that's high alpha, something that's low alpha, something that's high alpha, something that's low alpha, something that's high alpha, high alpha, high alpha, with a bit of low alpha. I start having. But more important, I am now able to compute this. Using a potential, I can compute if the orbit, which are the stars that are in the bar orbit. The bar is a structure. It's not a stellar population. As we said, I said somewhere, I don't remember, it's in a colloquium or whatever. It's not a stellar population. Stellar population is for example, what I show you, the star formation history in the inner part, here and there, these are stellar populations, right? The bar, no. The bar is a structure, a dynamical structure in the inner part of the galaxy. So I wouldn't expect that the bar has a stellar population typical, right? But in the field, for other reasons, it was expected that all the stars in the bar are low alphas, because the bar is made from the disk, right? And so the disk is low alpha, so the bar should be metal-rich low alpha. And these results telling me it's not the case, okay? So to say if it's true or not, what do I have to do? I have to compute the orbits of stars and to see if they are in bar-shaped orbits. This is a difficult job because, as he said, the potential is difficult. And so that's why you give a probability, because there are uncertainties everywhere. So you cannot say, this star is really in the bar. No, you can't, because you have uncertainties, you have this and that. That's where you spend the 90% of your PhD. It's like uncertainties on the problem, yeah, and then, okay. So we paint this with probability. So somebody's red here means we are confident this star is in the bar. Somebody's blue, we are very blue, we are confident the star is not in the bar. That's what it means. Now, look at this diagram. This is where the bar is. But you have stars on the bar, stars that are not on the bar. It's always mixed. You are in the center of the galaxy. You have a coeval place where everybody's there. So that's why. So you have stars on the bar, stars that are not on the bar. You are seeing this. You're seeing that the bar is more here. The stars that have high eccentricity and low Zmax. That's where the bar should be, actually. So, and then you see more. You see that there are stars on the bar, both at high alpha and low alpha. It's not that all the stars on the bar were low alphas. So that means there is no chemical segregation on the bar. That's how we say this beautifully, okay? There is no stellar population bar. There is structure bar. Therefore, there is not only metal-rich stars, but there are some metal-poor stars on the bar. Now, it's beautiful, because now you can go to this low part here. These are the stars that are the candidates to migrate. Because it turns out that to migrate, you need to be in cold orbits. You need to be in low Zmax orbits, okay? So who is in low Zmax orbits? These people down here, because this is Zmax, right? So all these stars, they are candidates to migrate. But a lot of them are here in the bar. And the ones that have high eccentricity, they are the ones that migrate more easily. So I have a reservoir of stars ready to leave the bulge, okay? And if I go like up, when I go up, so I call them migrator candidates. In the bulge we are. And if I now go to the stars that are at high Zmax, I'm getting rid of them, of the bar. I'm getting rid of them. And I start seeing, and I'm getting rid of the disk, because disk is low Zmax. And who I'm going to see when I go up? Some halo passing, but I'm going to rediscover the spheroidal bulge, which is buried there in the middle. I cannot see with all this mass in front, unless I had the age. If I had the age, and if this structure is very old, then I would say, let's plot everybody that's older than 12 gigayears, then they will appear beautifully. But we don't have the age in the bulge. But I think the bulge is there because of the structure, okay? So I see most of them are bulge. Bulge understood as a spheroidal component, high velocity dispersion, low rotation, okay? But, and they are, the guiding radius of the orbits of these stars is between 1 and 2 kiloparsec, really in the center. By the way, if there were stars there between 1 and 2 kiloparsec, with this extinction I show you, I would not see many. So to see them, I need them to have eccentricity to come out here so that I can see, right? Because I have a hole, remember? In the middle, I have a hole. Okay, so let's take that part of the down part of the diagram that we were just looking at, low Zmax, okay? The migrator candidates. And now we say, what is the typical metallicity of these stars? That's what I wanted to understand. Do we have enough supermetal-rich stars there so that we can understand the ones we are seeing here, that they came from there? And now we take them and we plot their metallicity distribution. This is amazing, to have a metallicity distribution function ordered by orbitus in the bulge. It's like creme de la creme, very beautiful. And then we have here the stars in the bulge that are on low Zmax, that are not in bar-shaped orbits, I know already. They are thin disk-like, okay? They have a metallist distribution, metal-rich. They are peaking at a bit below 0.2, okay? So it's the gradient. Metal-rich thin disk is the gradient, peaking there. Now I have these ones here. They are amazing. A lot of them are in bar orbits. Some of them are not, okay? And they are dominated by metal-rich, huge metal-rich stars. The peak here is even more than here. I put the line after, but it's 0.25 here, the peak. But I have a huge amount of more metal-poor stars also here, because the bar is not a stellar population. The bar is a structure. And if there was a node population there already, which is the bulge, it would have trapped some stars in this structure. So the structure is not only made of the disk, it's made for whatever was there, which is telling me maybe the bar was formed after then the bulge, spheroidal bulge, okay? So this is the metallicity distribution. So for our interest here, I have found a clear reservoir of metal-rich stars in cold orbits. The migrators are ready to come here, okay? And there are many. And their metallicity match the ones that I'm seeing here. And this is so beautiful, okay? It's my birthday gift today. Okay, now I look to the ones that go high in Zmax. Before I look to the base, now I'm going up. What happens when I go up in terms of, so I get rid of the people that are in the bar. I get rid of the people that are in the disk, the thin disk, but I'm get some thick disk. I'm going to get some thick disk, but I'm going to get the bulge. The thick disk will appear more in the window that is rotation. Here I have very high eccentricity and very high Zmax, and that should be a very high dispersion velocity population. And in fact, they have high velocity dispersion population here. But what I'm interested today is on the metallicity. Then we were here, right? In the other I show you, we were here with this metallicity distribution function. And if I go up, what happens? These people are going to disappear, and I get this population here. It's a metal-poor population that is bulge-like. It's a spheroidal metal-poor population. And this is not the metallicity of the spheroid, because apogee is biased to more metal-rich stars. I'm missing to see the metal-poor stars, but I know that if I see this much, there has to be a peak in the metallicity distribution that's close to minus 1.3, minus 1. And who is there? The globular clusters of the bulge that Beatrice just came here and explained to you. That's where the bulge are. The bulge is. So that's the globular clusters sitting on this population, right? And we're going to see this in a while. So the oldest stars of the Milky Way are buried in the center kiloparsecs. And you say, how do you know the age? I don't know, unfortunately, because our mission for ESA was aborted. But in the future, we will know. But I have the globular clusters of Beatrice Barboux in the bulge. And that we know, the oldest globular clusters so far found in our galaxy are exactly those. They are not at minus 2.5 like the in metallicity, like the ones in the halo. They are minus 1, the ones in the bulge. Very close to this peak of metallicity that I'm showing here. It's so beautiful. And then I say, we are seeing our galaxy at redshift 5 then. Yeah, that's where you're going to find them. So this brings you to a nice place, because if the ages of these stars are 13 gigayears, 12 billion years, this corresponds to redshift 5. If you want to look to these stars, were there when the JWST is seen at redshift 5, they were already here. You see, there, or whatever, in time, right? So it's like we are seeing our galaxy at a high redshift. So these are what we call the local counterparts of the bulge we are seeing with JWST. And then because they are too old, then they are called this population tree, interesting stars, because if they are so old, they are showing me the gas from which they formed 13 billion years ago. And today, we know what a supernova type 2 does. But were the supernova type 2 doing the same at that time? Were they more energetic? Were they doing weird things? Were they doing some things that not happening anymore because there the metallicity was very small, and now we have metallicity? So this could have changed the story. And actually, I have a publication where we were studying fast-rotating massive stars in the early universe that would produce chemistry that a normal star not rotating normally wouldn't produce. And we thought we saw them in the bulge, me and Beatrice and the group of Geneva. And that's when we published our Nature paper saying we found imprints of supermetal-rich stars, massive stars fast rotating in the bulge, you see? So this is another window topic. I don't have time to talk about this here in these lectures. Other group, Heidelberg with Hans-Otto Rix, also were studying these stars. So these are more or less like we did, high eccentricity orbits. They are plotting here with apocentric. So this is stars, so the radius, the farthest radius that in the orbit. And you see that these stars that are here, the ones that are debris, they have very large apocentric. They are passing just in the bulge. They are not in the bulge. It's the same plot we are showing. But this is the bulge, the old spheroid. So essentially what I'm saying is this. In the bulge, so this is the metallicity distribution of bulge stars. Forget about the halo right now. But that means that in the bulge, the metallicity versus time increase very quickly and are reached solar and above solar in less than 500 million years. Less than a giga-year, for sure. Okay? This is the age-metallicity relation in a model, chemical evolution model, to fit more or less the distribution of metallicity in the bulge. And this would be in a more slow evolution, like for the halo. This is a paper that we never managed to write, but it's there. So if I compare the alpha over iron versus iron plots in the bulge and in the halo, for example, for two different models, I will have that for the bulge, I will reach high metallicity in short time scale. And here these points are lancing stars that were in the bulge, for which people manage, because when a star is lanced, then it gets brighter. Then they manage to see dwarf stars brighter in the bulge and put them in the CMD and get the isochron age. Difficult job for a couple of stars. But then here I'm plotting only the very old stars that where Bensby found the old stars 11 giga-years. And I found many here, you see? And it's fitting this kind of idea that you can push the metallicity very quickly and make the bulge. And the R Lyra is also the old one. When I go to R Lyra, like yesterday I think in the colloquium I said this, R Lyra are 10 giga-years or old stars. So that's a way, like you don't have the age, but you have an R Lyra, then look what the R Lyra is saying, okay? The R Lyra is giving a similar result. Okay, so I will finish now with the globular clusters. Because, as I said, I don't have age in the bulge. I think I'm seeing a very old population there. There's a lot of implications, because that could be a reservoir of population tree stars doing weird things, so nice to do things. And also is a reservoir for stars coming here. That's two things that I'm interested in. So let's do the globular clusters. So Beatrice is the expert on globular cluster with her collaborators, Bika and Ortolani. And by the time we wrote the review on the bulge, 2018, this is L and B, largely to the north, is the box on the sky, okay, of that inner part. And this is where the several globular clusters were located. And then different techniques. And she came here to you and probably showed their new paper, where this is the, look, these are a lot more. This is the pace it goes, because we wrote this in 2017, was published in 2018, and she comes here with this in her paper. So this is, a lot of these new clusters were observed also thanks to a fantastic survey, photometric, that is the VVV survey in the infrared, that you can peer into the dust, right? So you have a lot of globular clusters. Most of them, the new ones, come from VVV. Now, same box, extinction. It's a different way to show extinction, EB minus V. That means this part here, very close to this 0 in B, is dust. You cannot see things here. It's always this hole we have, unfortunately. And we don't have Gaia and whatever. And these are some globular clusters around. And Beatriz and her collaborators studied this list of, and in one of these I am also, these are the globular clusters in the bulge. Where are them? Look where I'm going to plot them here. One is here, there, here on the board, like the maximum you can do, because beyond that you can't, and there. In the bulge, but you can still get optical spectroscopy. And they got photometry from HST and chemistry from UVIS, 8-meter telescope, high-resolution telescope. Thanks. It's very good to have good collaborators like them. Amazing. So Stefano Souza was a PhD student of Beatriz. Now he's a postdoc and came also to stay with us 1 year at IP. Amazing student. For example, here I'm showing you one of the globular clusters. This is the field. Now, it's amazing to study clusters now. You have proper motion. So you can find immediately who is a member of the cluster, who is not. You just look here. He plot proper motion in one direction, proper motion in another direction. A lot of stars. And you need to do the member, because you're going to ask time for an 8-meter telescope to sit in there 8 hours to observe a star with high resolution. You better know this is the star in the cluster where you think it is. So this is a whole machinery also from Gaia. Clusters is the thing to do. Okay, so they have stars there, and he got the abundance from there. Now, in this paper, we put the things together. Very beautiful paper. This kind of papers that you can do nowadays, where you join all the techniques. Very difficult for the students, because you have to handle all the things at the same time. Stefano knows how to work with HST, CMD, a spectra from UVIS, and compute the orbits, whatever. You see, I'm happy I'm not doing PhD now. So we go back to our box, and we plot the clusters for which we have good ages, because we can get good ages from this data that Stefano has worked. So look where they are. They are here, where we are getting rid of the bar, and we are going to see the oldest population in our galaxy. Nice. Here, I'm also plotting the bulge R LiDAR. I have a lot of bulge R LiDAR also in different orbits, because I have also, as I show you in the colloquium, R LiDARs on the disk. You know, not everybody's in the bulge. So you see here, you have some R LiDAR here. So now I'm going to compare the metallicity distribution of our stars, where their stars, their globular clusters are. And you see they are below -1. Most of our stars, the R LiDAR is this ones. Most of them are close to the globular clusters. They are old, and they are saying, we are here. We are the spheroidal component. You are not seeing us because you're looking to the whole thing. And because you're using apogee, where we don't reach us in metallicity. You're seeing the tip of the iceberg only. But if you want to see us, you have to be at this metallicity here, and you have to know that we are the older ones. Otherwise, you're not going to see. That's what's happening here. And then, what else? Their guiding radius, their mean radius in the orbit is 1 and 2 kiloparsec. We are here in the middle of the galaxy, you know? That's what this is telling you. And you have UVIS. So now, Stefano goes there, measure the spectra for some stars in the globular cluster. Globular cluster has the age. The age is 12.7 giga-years. It's just like after the Big Bang, okay? They go there and measure. Oh, look, these ones are the alpha elements that they managed to measure: magnesium, calcium, oxygen, silicon. Then it's not enough, because we always want more. He measured the iron peak elements, the elements that follow the iron here, you see? Vanadium, chromium, manganese, iron, beautiful. And we want more. He measures here. He got from apogee spectra, right? He has also cerium. Then it comes these weird elements, neodymium. You know, nobody ever talked about neodymium. Turns out that became very popular because the apogee spectra is great, but doesn't have S and R process elements. The only ones that appear are neodymium and cerium. And so They are nice because they are S-process elements. They are making shorter time scale. So they are good to figure out the chemistry of a stellar population. And now he can plot this. Alpha over iron versus iron, where alpha can be different things, elements that add alpha particles. They are the ones that type 2 supernova do. Oxygen, magnesium, silicon, calcium. And these are the stars in the Milky Way, in our RPM sample, not in the Milky Way, in the box that I told you about, the paper of Anna, the RPM sample, the one that I used the proper motion to get there inside. So these are our stars. We have the low alpha, the high alpha, as we have seen before. And they are extending the metallicity. As I told you, we were not reaching that metallicity. And their globular clusters sitting here. And look, they are beautifully following where we think the end of our distribution here. They are beautifully following here, you see? But they are globular clusters. And there is an extra complication. I don't have time to talk about this, but in globular clusters, the preserved gas composition can be changed for some elements, because nature is tricky to us, you know. And there is, so far, the globular clusters have two populations, the first and the second population, and one has changed some elements, but just a couple of elements. There is the anticorrelations in chemical abundance in the globular cluster. You have to know that, and you have to say, oh, I found the magnesium a bit low. Well, don't worry, it's the globular cluster, you know. And so that's what we do. But, and here is plotting also the R-LiDAR. This is the beauty of the data today. And we see that for the iron peak also, the globular clusters are where they should be. Manganese versus iron, they are where they should be, meaning they are the continuation of our population that we are saying in the other paper is the bulge old, they are there. And in copper, they are there. So we will jump this. This is too complicated. Forget it. What is important is this now. Finally, I can trace the age metallicity in the bulge, which I cannot with field stars, unfortunately. With field stars, I can do something with the cluster. I can't, which is see the different stellar populations there, the thin disk, the thick disk, the bar, whatever. This I can do with the field star. I cannot do with the clusters much. I can do some. And this is what you're seeing. Iron versus age, like the chemical evolution model I showed you before. And you are seeing this fast increase, less than 1 gigayear, shoop, and it's going up. And this here, focus here, minus thing. You have a lot of these stars. The clusters of Beatrice are around -1 here. You see? This is what's happening. But you have also this other thing here, clusters. And this is what Beatrice discussed, I hope, with you, are the excitoclusters. Because as discussed yesterday in the colloquium, galaxies are falling into ours, and every galaxy has also his globular cluster system. So he doesn't come only the stars, he brings together everybody. And so here we have not only the stars that are migrators, but also extraterrestrial, extra galaxy stars, so the excito stars, and the globular cluster is the same. The globular cluster from here, the globular cluster excito. And you're seeing them. And they have a different star formation history. I have shown in the colloquium that the star formation history of Gaia Enceladus and Sagittarius have low alpha over iron versus iron, because the star formation is lower than this sort of thing here that we have going on in the bulge. Because you need potential well to make this boom of star formation. And that's what you're seeing. So it's very beautiful. I'm going to finish this with this final thing here. One thing very much discussed in the literature that links the Milky Way to what's going on in the other high redshift universe is the fact that with ALMA data as well, not only JWST, but ALMA data as well, and JWST, they are finding very old globular clusters in other galaxies, essential bulges in other galaxies. And they are seeing also what is called clumps of star formation. Pieces, when you look to the high redshift, you see pieces of 10 to the 7 solar masses, clumps of star formation. Because now I am there. These stars form one day, right? The stars that I'm seeing here that are today 13 gigayears, they formed somewhere one day. Now I go there in high redshift and I see, do I have this crazy star formation somewhere? And then they see clumps of star formation, crazy, a lot of star formation. And they see them in not only in the inner parts of the galaxy, but also around, in a sort of disk. What is this disk? The thick disk. Because I told you, the thick disk is also old. And we believe that the thick disk and the bulge are forming at the same time in our galaxy. And there, these clumps are seen thick disk and bulge. And there is a model, of course, there's always a model, where people have run simulations where these clumps, which have very high star formation, they coalesce and end up in the bulge. And that's maybe how our spheroidal bulge was formed. So that is very important. They need constraint, we need constraint. And so that's giving. Are we seeing these buried past accretion events and these clumps in our galaxy? We think we are, okay? And one of the models that came out from De Battista and his group is they predict in their clumpy bulge simulation, I mean, to be taken to a grain of salt like this, because you saw simulations, how complicated this is. They believe that they have seen that oxygen over iron versus iron for those clumpy bulge should have this behavior. This behavior is very similar to what we are seeing in the middle of the bulge when we get rid of the bar and the disk. We are seeing more or less the same thing. But in their paper, they didn't read our paper very well, or they didn't read at all. No, they read because they quote. They finished their paper saying, this is the prediction of our clumpy bulge. But the paper of Queiroz sees this. Therefore, if their data is correct, our model is wrong. Because we don't see this lack of stuff here. But when they compare to us, they compare to the whole box. So they didn't read that what they have to compare here, you have to go up to do what the job I did with you. Go up, get rid of these people, and look the old bulge, right? So they say, if this data is correct, our model is wrong. And when I look to their model, I say, wow, the model is selling what we saw in the data. So I call him, say, can we have a telecom? I think you didn't understand our paper. And then we had a telecom with Anna and I say, look, you shouldn't look to the whole box. Just look there. And he's like, oh, I'm sorry, I didn't understand. Because, of course, we are all in a rush. It's very difficult. That's what you do if somebody is not agreeing with you and if you believe you understood why. You don't get pissed and say, oh, this guy said bad about our paper. No. It was nice. And now we are collaborating, hopefully, if we find time, to kind of try to relate our data with their models, right? So that is also something I wanted to make clear here, because nowadays there's so much data, people have so few time, and people start fighting without a reason. There's no reason to fight. It's astronomy, and is everything so beautiful and nice that is what we want to see. So we know from recent orbital analysis that we do have a mix of population, and if you want to look for this population, you have to take that in account. That's my answer to him. And so I leave here the key points of this lecture. Gaia plus spectroscopy made it possible that we do good distance in the center, to the point that we saw this velocity quadrupole beautifully in the center of the galaxy. The bulge now can be studied in orbital space, which makes very important things. Caveat, very good point, is the potential. Because potential depends on how much we understand the galaxy, but you cannot wait for the perfect situation to start working. So in the paper, there's always a section, caveats. Be sure you put that section, caveats. And then the globular cluster objects, there are objects confined to the inner 4 kiloparsec that are meta-rich enough to migrate here, and they will migrate, and we will see them in the next lecture. We find that no chemical segregation, that's the way beautiful you say this, no chemical segregation in bar-shaped orbits. That means everybody's on the bar, right? And we need to move on in the future to get more data, and we need Gaia and infrared. That's the bottom line of this. And we are making an IAU symposium here, stellar populations, to study all that. Here, I know, this is wrong. It's not at Rio de Janeiro anymore. Now it's in Paraty. And is in honor of Beatriz Barbui. State, yeah. Is in honor of Beatriz Barbui, who has contributed enormously to the field of bulge, but also to the astronomy in Brazil. So that's that. Thank you. So I'm sorry if today was a more complicated lecture, but I really wanted to dive you into this because
That's great.
it's
Excellent.
yeah.
Questions, comments? Could be in Portuguese, English, Italian,
English, Italian, German, French,
German,
whatever.
French, whatever.
Hi. Okay, so thanks for the talk. And I was just wondering, like, did you actually computed velocity dispersions for the bulge, like?
Yes.
And how? What were you looking at into?
They are like they should be. High velocity dispersion.
Yeah, but in terms of like kilometers per second, like 200.
Yeah, to the hundreds. Yeah.
Okay.
In the paper, we have the same plots that I show you for metallicity and alphas. There is also for velocity dispersion. There is also for guiding radius in each window. Also, although the people thought it was a long paper, and it was, because nobody has seen this data before. So we have the first part talk about the whole box, second part going into these 8,000 stars. So that's why it's a long paper.
Okay, thanks.
And it took 1 year to be accepted. And we didn't change anything. It was just, we had a tough referee. It was James Binney, which is an honor, of course. It's a person that is the person that understands dynamics. No? And the main point is the potential. So we had to do some simulations to show that we are knowing what we are doing for the potential. No? And the third author is the Ángeles Pérez Villegas, who is a dynamicist. She's excellent. And so she is, that's why another point, combine the expertise. I'm not a dynamicist. So I am the chemical and data. She's the dynamicist. Anna was the PhD student, amazing. And these three girls, plus all the people together with us, made this paper. I'm proud of it. 3 Latin American, actually.
Hi, thanks for the nice talk. You showed a graph with the alpha enhancement in ferro. I don't know, with the metallicity, and then there was 2 regions, right? 2 defined, separated.
Yeah,
yeah, like this.
This one, yeah.
Yeah, but I think that was already the bulge only. So the bulge has this.
Yeah, it's bulge only. No, up there, you mean, when we went to bulge only?
Yeah.
So that's the part we still need to investigate better. Let me go there quickly. Good point, actually. Wait. Where they are? They are here. Wait a second. Here. So when we went up to get rid of, and we are here, yes, we have that, right? We are above, we are still some high metallicity here, and low metallicity, the more metal poor here, where actually the globular clusters of batteries are. So was this a contamination of this population here, or was this really also very pristine old stars at low alpha? And according to the clumpy bulge, that's why I was interested on that figure from the theory, because I need more data here. Now I'm working with a new sample with my current PhD student to exactly give this answer. But when I look to this, I saw that there is stuff here. And now there are 2 papers talking about the knot. They are thinking that there are super meteorite stars, really like very old, very in there. There also we are not agreeing fully, but yeah, let the data tell us more. But
thank you.
Yeah.
Thanks for the lecture. Could you explain the picture of the quadrupole in the
that is the tough
bulge,
one, because, yeah. So, where is them? This one, right?
Yeah.
So essentially, you can see the bar as a rigid thing that is turning like this. So you are seeing the radial velocity of these stars from here, right? So depending, the bar has an angle with respect to us of more or less 20-something degrees. And so imagine this cigar, like if it was a cigar, rotating. And so the radial velocity that I'm seeing, up, down, I mean, one I am going far away, one I'm coming nearby. And that's why in the end, I'm getting this kind of, this is part of the reason. The other, but there is a better way to explain this, which is a really dynamical way that I'm sure Angeles can do better than I. So I don't think my explanation was very good. But if you have a bar there in radial velocity, this is like the signature that you're going to see. Because the bar, there's also a now simulation showing. This one, you see this. Now you don't see very well. Because the bar, it's here, connects to the spiral arms, right? When you see a galaxy, the bar is connected to spiral arms. And this connection also, I think that's what is also the streaming of the bar. I mean, there is this connection with the spiral arms. And you see this, when it's turning, you are seeing this. The spiral arms are rotating, right, also. And the bar and spiral arms do not have the same pattern speed. And so this is what creates also these resonances. And so this will translate. If you didn't have a bar, you wouldn't see this. And if you do have a bar, you see this kind of pattern. But it's more complicated, and I'm sure I've explained not very well, and Angeles is the person to explain that better. Actually, this plot convinced the referee that we had good distance, essentially. No, I just want to say that the globular cluster age that is done from photometry, from HST photometry, are very robust. So the error bar is like small. That's why you can do this age-metallicity relation. It's beautiful. For field stars, this will be very difficult to do. So that's why it's really nice to have Beatrice here leading that topic. Yeah.
More questions, comments? It's your last day, right? You
no,
come have
we
tomorrow.
have a last lecture.
Yeah, so I have one day more. Well, I have two comments about that. The first one is about exoplanets. I mean, along this meeting, we tried to connect exoplanets with all these universe of data, etc. So in population, there is some awesome stuff. We need to know where are the first generation of planets, and we need metals, right? So can you
Exactly. So let me take the advantage then, 2 minutes. Yeah, because these cool look like they are disconnected things, but actually I connect them very well. So first of all, we said population 3 stars in the center of our galaxy, so this is very old. Who was contributed to the chemical enrichment? And then we see some chemical elements, and we have to explain them with these fast-rotating massive stars. But another option is neutron mergers, which is one of the lectures here too. But the neutron mergers, the discussion is it takes some time to merge. And this is 500 million years, very quick. So this is also connecting to, we are waiting. So the gravitational waves were discovered. The neutron production was when they could see who was exploded. They found the neutron production of neutron capture elements. Now we need the rates so that we can see the impact of this. This will come in the future. So this has a link. And the other link is with planets. Always we have to have a link with planets, by the way, nowadays. But look at, I was thinking about this. If I had a project, if I would do a planet project, I would tell people, look if there is a planet next to the supermeteor-rich stars. Because then you could say, I found a planet in the bulge. You see? Because I'm telling you, the star came from the bulge. I mean, I don't know if the star came with the planet, but I guess it will come with the planet. That is for somebody to compute. So let's do a paper where we discuss if the star can come with the planet. And then the metallicity is what you ask is the metal poor regime.
Yeah.
Okay, but
Top
in the
three.
metal rich also.
Same.
Could we have a planet next to a star that is 3 times the metallicity of the sun? We don't have yet a planet
No,
around a
guess not.
supermetal-rich star. Because supermetal-rich stars are rare, right? But they are less and less rare because now in this other lecture I'm going to show you, we have millions of them because of the Gaia. Can you look for planets around them and tell me if you see a supermetal-rich stars with a planet? That would be very nice because I can tell you this star is not formed here. And then we can say, oh, we saw a planet from the bulge, which is impossible to measure a planet in the bulge. But we had this gift that the star is here next to us. So that could be a connection, right?
Yeah, good. I mean, we see with Vladimir that the disk instabilities need metals. And for the formation of planet, actually, it's a problem for planet without metals. So
Yeah.
that is why POP3 is kind of challenging stuff.
Yeah, that's also interesting because we now find also very metal-poor stars here. But those, yeah, you can measure and see if you have planets, I guess. But I guess Plato, that maybe.
Oscar, yeah.
Yeah, but they have an input catalog that's very much solar. And that's why I'm also wanting to contribute to put there some metal-poor stars. And so inside Foremost, I'm doing the calibration stars for Plato. Giants I'm putting, yeah.
So more technical stuff. How you know the rotation of these POP3 stars? Because you mentioned that.
Yeah. So essentially, I don't know the rotation, but I know that nitrogen should be made as a secondary element, meaning that you already need to have C, carbon, oxygen, and then nitrogen will need time to be made. And mostly, the stars that most made nitrogen are low-unity minima stars. However, when the UVIS telescope, the UVIS spectrograph came light in the 8-meter telescope, when Xpit from Meudon and Cairel from Meudon had the first stars, they start to measure chemical elements at very metal-poor stars, -3, okay, instead of solar. And the expectation of normal chemical evolution model is nitrogen over iron will be low, but they were high. The expectation will be carbon-12 over carbon-13, which is also something you can use, will be high, because carbon-13 will need time to come, and it was not. And so when I had this data, I said, what? Then I knew that the group of Geneva was producing the first stellar yields, so how much a star will throw from an element, and they had a star with rotation, without rotation. And they are saying, in the very early universe, when you have less metals, the star is compact, but because of conservation of angular momentum, it will turn very quickly. When it turns very quickly, it leads to mixing stars, and this will dredge up, and this will produce nitrogen primary in the star. And this is not being taken into account by anybody. Then I made a paper saying, I used the stellar yields of these people, and I see that I could have a little bit high nitrogen over iron not fitting the data, but still not fitting the data. They use 300 kilometers per second for the rotation. I think they need 800. Because if they know 800, I scale more or less their yields, and I think I have that. Then what happened? They got upset again, because they said that I used their yields, and they am showing that they don't fit anything. No, that was not the point. I said, no, you actually have the only yields that are going to the direction of what I'm seeing. But I'm just seeing this star should rotate faster. Then, in the same place where I am presenting this in a talk, no, in a poster, next to my poster was the PhD student of André Médère and Georges Menet, which was at that time Raphael Hirsch. And he had computed some stars at 800 kilometers per second. And I had a plot of the stellar yields that they had computed and what I need. And he had a plot of the old yields and the new yields. And when we look, we had the same. And then I decided to join Geneva, and I moved there, and we worked together in the fast-rotating massive stars imprints. But that's why we don't know the rotation of those stars. They are dead. But we know that we need certain rotation to produce certain amount of chemical elements. And we worked for 2 years together. It was a fantastic collaboration.
Amazing history. Okay. Short question, probably finish this tiny disk in thick disk diagram that you showed before.
Yeah.
Yeah, just to.
Here we are in the bulge, but it's still the same.
The next one, yeah. But
you mean
I
the
would
big
like
one?
This, yeah, with the 4. I mean, it sounds challenging. Divided thin disk and the thick disk, right? You put a line in some diagram, just
Yes.
a line like
Yes.
that. So
That's why I don't use the line anymore. I mean,
yeah,
people are using the line because you can put a line here, depending on the data set you have, but some data sets you don't have this gap. Actually, this is a KDE distribution. If you plot each point, you're not going to see this beautiful. So this is the density
Diagram, yeah.
probability distribution. But this is the next paper, and maybe something about this in the next
so
lecture.
I have a student Natal that's just finished the PhD. It's Moisés Pereira. We try to figure out what the best function to fit that.
Yeah, you can.
Because at some point line is not good, but you know it's.
Yeah, you can do this. So what I did and what I'm going to show in next lecture is that I am now using some machine learning stuff.
Yeah.
And so, for example, here we are looking alpha over iron versus iron and seeing where there is a cut between high alpha and low alpha. But there are a lot of elements in the periodic table, right? And so the TSNE, which is a reduced dimension algorithm, I give to TSNE a bunch of chemistry and let the TSNE say, find me populations. Look into the chemistry. The TSNE looked to 20,000 combinations. Because I have, for example, when I have a very rich data set that has a lot of chemistry, then I put the TSNE and say, this is divide for me. And then the TSNE beautifully tells me, this is the thick, this is one population, this is another population. And I look them, and I plot them here, and then I find the thick this, the thin this. This is very beautiful. This was the work of my other PhD student, Friedrich Anders. He did one paper by that. And I will show something about this when I will discuss in the next lecture the supermetal-rich stars that are here. And we are going to find them like this, using TSNE.
Thanks. Let's thank again, Cristina.
Thank you.
Coffee break time. Enjoy.
I will leave my